Next up will be Christophe talking about Elixir, at or in or on or for or some appropriate preposition. Anoma.
Yes, so four distinct parts. First part, picking a language when you're designing something from the ground up. The second part will be about transparent network addressing, which is something we do at in the Anoma application, and this is particularly interesting because we are working with what language would we have chosen. Then I want to talk about examples, and not particularly examples about something, but the notion of examples. And finally, macros, because you cannot not use macros when you have a language that supports them. So when you pick a language, there are a few things you can take into consideration. The most obvious one is it looks like a fun language, not the best choice, but another option could be because you know it well. And if you know a language well, that means that if you want to start building a prototype or any product, you'll probably get there faster. And then maybe the most sane choice would be picking a language because it can express your problem domain very well. Or maybe you want to maximize maintainability, which kind of ties in you know it well. For example, if you write your application in COBOL, you're going to have a very hard time finding people to actually maintain that application. Maybe performance matters. So if you want to do some number crunching, you might want to, and I'm sorry for saying this, look at Python with all the NumPy libraries and what have you, or because your boss told you to use said language. I personally wasn't part of choosing the language for Anoma, but I can speak to why it was eventually a good choice. So the way it kind of works within Anoma is we have a specs team, and they define shiny theoretical models, and then the engineering team has to implement them and maybe give some feedback on them because it's not really implementable or something. And eventually you reach a fixed point, and then the engineering team can implement a proper theoretical model. So at the core of the Anoma application is an Anoma engine, and so at the top left you can see the Juvix definition of an engine. Doesn't really matter what it says. This is the important part. So the behavior of an engine tells or defines what an engine can do to its environment, which messages it can send, which engines it can create in turn, or how it manages its timers. So for those of you who know Elixir, it's pretty obvious what this thing is, but we haven't chosen the language yet. Another few things that you might want to take into consideration when picking a language are debugging facilities. At least the stepping debugger is nice. They've had it since the 60s, so why not today? Proper basic tooling, which for me personally is really important. There are some languages, I won't name names, JavaScript, the tooling is reinvented on a weekly basis. So you start your project, you use some of the tooling around it, and the week after that somebody invents a new tool. You can either stick to your tool, or you can switch to the new tool because it might have features you actually want. If you have proper basic tooling, all the development effort is focused within that tool, so you'll always just have the nice and shiny thing. And then finally, this is where is Jeremy. He's the one that got me into these things. So interactive systems. An interactive system is an application that when you run it, you can actually inspect it, you can manipulate it, and you can basically play around with the system. A C application, for example, runs from start to finish, or I don't know, runs in a loop, but it's not an interactive system. It runs and that's it. So if we now look at one of the core concepts within Elixir, which is a gen server. So a gen server is a process that runs from start to finish, but usually it never finishes. And it keeps track of, can I point? Yes. It keeps track of internal state. And this state is isolated within this process. In this example, it's a stack. So nobody else in the system can poke at this state. It's owned by the stack, and only the stack process can actually manipulate it. If you want to have access to this state, or you want to manipulate it, you use calls or casts, which are message sent to this process. Please manipulate the state, or give me access to your state, or a part of the state. The nice thing about this is no race conditions on your state. There's only one process responsible for managing it, and all the messages you send to this process are processed sequentially. So there are no race conditions within a single process. Of course, you can make complex systems where it becomes muddy, but the essence is this is really useful. So I guess most people already know we implemented Anoma with Elixir, and all the engines defined by the specs people are represented by a gen server. And so the thing you see here is the observer application, which is built into Erlang, and it allows you, because it's an interactive system, to look into the system while it's running. And the gray boxes are all gen servers, and there's a hierarchy between them, but that's not really important now. And they all represent one single engine without much changes with respect to the specifications. So that's a lot of explanations to say that engines really map well on the computational model of a gen server. So, of course, we used yes Tobias. Thank you for cheering. So, to summarize, we chose Elixir because it can express our problem domain really, really well. It's a fun language. The boss told me, because I wasn't here to make the decision. It's an interactive system, which is really, really nice to work in, and I wish everybody would do that. And it has proper basic tooling. There's a mix tool, and that's it. So nobody's inventing new tools every week, you just use the mix tool. The one thing that we don't have are debugging facilities. Like, we do print statements like peasants. But maybe one day. So, I explained to you why we chose Elixir. And now I want to go into a few of the design decisions we made that were kind of only possible because we were using Elixir. So we're building the Anoma controller. So it's an application where many instances of this application will eventually connect to each other using a consensus algorithm, perhaps, if Jamie ever figures it out. And as is part of every software platform, you need to test your system. So how do you test a distributed system? Well, you could set up a very complex CI pipeline with external tooling to spawn up multiple instances of your application and test it somehow like that, but we don't want to. We're using Elixir, and we can do everything we want within Elixir. So we're just going to try and do it like this. But there are a few problems. So here you can see a diagram of two. So let me first explain. A Beam VM is an instance of the Erlang virtual machine in which an application can run. And the application we are designing here is called the controller. And maybe Joe has a controller and Mike has a controller, and they want to communicate with each other. So the executor of Mike can send a message to the mempool of Joe, please give me the list of all your transactions. Because these are two separate physical machines, this message goes across the network. But at the application level, we don't really want to deal with sending a message across the network, sending it to a local engine. We just want to talk to an engine, and that's the abstraction level we want to design our application at. So in another case, we have a single machine that runs two controllers. So again, we just want the executor to send a message to Joe's mempool, give me your transactions. This all seems pretty easy when you look at a diagram, but it's actually not that easy to do because there are two completely different types of communication. This thing goes on one single machine, the chance of network failures next to 0. So how do you send messages to processes within an Erlang machine? So I hope this is readable. You start up a gen server and you give it a name. So let's assume here we're talking about a mempool. The name of this process will be mempool because the module translates to mempool. And if you want to send a message to this mempool, you just do a call to whatever process is named mempool, and the message will arrive. But you can only have one name for one process, because it would get confusing if you have two processes that say I'm mempool. So that will cause problems. So given the default way of programming gen servers, we can have multiple controllers on multiple virtual machines. That's fine, because one machine has one mempool process, and you can find out where these processes are located. If you have a single controller on a single virtual machine, that also works fine, because again, you have one mempool. But because we want to test a distributed network of controllers, and we want to have this transparent network addressing, that's not going to work for us because we want to have multiple mempools on one machine and multiple and one controller spread over multiple machines. So we needed a mechanism that allowed us to basically send a message to a mempool from a given identity and just make it so. This would seem to be a lot of work, but there's the built-in library registry, which allows you to register processes wherever they're located in a distributed system. You have distributed Erlang, which is, well, one of the main reasons people look at Erlang, and a little bit of custom extensions we wrote. And by a little bit, I mean a few dozen lines, so not that much. So if we take our previous code, 2 changes need to be made. Instead of using a name, like just mempool, now we request a name using our name, so Joe or Mike, and the name of our process. Yes, Jamie.
So just to be sure I understand, you want to make the red crosses in the top left and bottom right into green ticks.
Yes, exactly.
And there are 3 boxes along the left.
Yes.
And just to check, do you need to use all 3 boxes in order to turn the crosses green?
Yes.
Or any one of them?
Yeah, sorry, so all of them. So it's a composition of these 3 things. But the important thing here, and I could have made that more clear, the first 2 are just built into Erlang and Elixir respectively. So they're just there. And this is the only thing we had to write.
But by the sound of it, you need a bit more data or something.
Yes. Yes.
Is it just that? The
Just
registry
that.
needs to hold
So
a couple of data types that it wouldn't normally
Exactly,
hold.
because we are dealing with engines, and an engine is identified by what is it? It's a mempool, and who owns it. So Joe or Mike. These 2 things uniquely identify for us globally where a process is located. So we just wanted abstractions that only take these 2 arguments. And I think so. We kind of abstracted over the registry because obviously it's more complex and more powerful than what we need it for. So we built a little abstraction on top of it. Where was I? Right. So using the registry, given a name and given the name of an engine, we get back an address where we can just send messages to. If this message is on the same machine, on a different machine, we don't care. We just write at this level, identifier and name of the engine. Using this, we can split a single controller over multiple machines, and we can run multiple controllers within a single machine. And what this gives us is we can now program like it's 1986, because within a single machine, we can just start up multiple applications without any effort, basically, and we can start communicating with them. This is a very trivial example, but in the context of testing your system, it's very powerful to just be able to start up multiple instances of your application and transparently run tests across a whole network of your application. So I think this saved us quite a lot of time up to this point. So, yeah. Then I want to talk about something slightly different, which are examples. And so there's Jeremy. He's the person who explained it to me. And I should mention here, so by examples, I mean examples defined by, I forgot the authors, but the paper is called J-example. So it's a notion that other people have actually invented, and we're just running with it. So everybody who has ever written any kind of serious piece of software has written unit tests. And what we argue is that unit tests are a treasure trove of information. Because in essence, what's a unit test? You start up your system, you do some kind of logic to create your system in a particular state, you execute some of your domain logic, and then you make assertions about the result of those changes. So they're little units, hence their name, of logic that are strictly defined and tested about their effects. And if you make a bug, then the unit test will fail. But given that these things are so small, they actually explain to somebody how your system is supposed to behave. There's just a very weird way of documenting things. And so we think that this information is too useful to just chuck into the unit test box and never look at them. But we're dealing with an interactive system. So what do we want to do? We want to take these unit tests and make them more into an interactive way of testing your system. So, as opposed to unit tests, examples are regular source code. So typically, if you look at unit tests, they're in a separate folder, they're not compiled in your application, and you just run them with whatever command test. And then if you get all green lines, yay. If you get red lines, you gotta find a bug. Examples also fail fast. So a big difference with examples and unit tests is typically in a unit test, you start with a blank slate, so to speak. You call some fixtures, which create an example user, an example data structure, and then you run your tests against these things. But we argue that these fixtures are also examples. So you will have an example, how do I create a user in my system? And if you then have an example that wants to, for example, test deleting a user, you'll call the create user example, use the result of that example, and then delete it. So let's imagine you have a bug in creating a user. Your delete user example will not even execute because it depends on the create user example, and that one will fail, and the other examples that depend on it don't even get executed. So you know immediately it's in the create user that something's wrong. And then finally, examples can be used to interact with your system. So this is actually where the value really is obvious when you think of them in an interactive system. So I have an example of an example. Within the Anoma system, there's the notion of an intent pool. So you submit a transaction to the intent pool and it gets executed. So you can obviously think we'll probably have an example of adding an intent to the intent pool. But an intent itself is created out of actions. And actions are created out of resources and so on. So you get a whole stack of examples. We're gonna jump in at actions. So this example here creates an action. It's not really that important to know what an action is. You just need to know action is a part of a transaction. So in this example, we call two other examples to create two resources. We create our action. We make some assertions about these actions. So that's, I don't know, something about delta and verify, not really important. And then we return the action. So if there's a bug in the action logic, this thing will fail. And the nice thing is, so yeah, not really readable, but at the bottom, it's a snippet from my Elixir REPL. If I want to play around with what's an action, what can I do with it? What does it look like? You want to take it apart, investigate it, just call the example and you get an action back that you can play with. A real action that actually exists within the system. So we have an example to create an action. Now we want to create a transaction. And to create a transaction, we need an action. Thank God we have an action example that we can use to build our transaction example on top of. So again, we call the example, we create a transaction, we do some verification of the transaction to make sure it's correct, and we return the transaction. Again, you just put this example in your REPL, and you have a transaction that you can play with. Final example. We want to add an intent to the intent pool, so we need to create an intent. We have an example to create an intent. We add the intent to our intent pool. We make some assertions about the system, namely, if we added it to the intent pool, it should probably be in there now. It should be in there now, and in case it is, we just return the note. Right, so yes.
Thank you for that. Property-based testing?
Yes. I've actually been meaning to try it. There's a very good library actually to do it in Erlang, but I quickly got the idea this is a rabbit hole and I have more important things to do. But yes, I think we should really use property-based testing for some of the things we can test here. Yes, I agree. Jeremy has a question as well. Sorry.
Thank you. So about property-based testing, if you don't mind me like hijacking your comment, I think you can do it in a very example-focused way by having the properties and the domains that you go over be an example as like an object that you can then see the results of and play with itself. So property-based testing would go very well with examples, because I thought about doing it myself at one point.
Jonathan had a...
I just have a comment, like following the same practice as you were showing before. Like in the input, like for example, in this function you have add intent, enode, and then intent is an example, right?
Yes.
Can you promote that to be an input for that function and use that as an example so you can run it,
Yes.
but also use the intent, same as in the previous example?
That's actually a very fair point. So I haven't been writing the best of examples, and I actually didn't notice, but I took the best ones. But indeed, so the idea behind examples is that you can either run them standalone. So all examples can take 0 arguments or arguments. And the point here is if you don't pass any arguments, it's an isolated piece of code that you could run as a unit test. But if you want to run it in your REPL, for example, and maybe you created the intent somewhere in your history, you should be able to pass it in here as well. So yes, it should be an argument, you're right. Okay. So examples offer us a couple of things that are very useful for onboarding people into a complex application like Anoma. So you can use them to get to know the system. Do you want to know how the intent pool works? Just run the example and inspect the system. It does require you to know the tools to inspect a running system in Erlang, but I mean, if you're going to do Erlang, it's best to get to know these tools. Examples are interactive, so as opposed to unit tests, you can actually use them to interact with your system. And if the examples fail, you quickly know where the failure is coming from. So I think this is the this is the last part. So rule number 1 of macros: don't write macros. There's actually more context to this statement, but in essence, it's true. So the rules with macros is, does everybody know what macros are? I assume so. Yeah.
Yes, I know.
Okay. So macros are, yes?
I think I know what it is, but I feel safe with you.
Okay, so in summary, a macro is a piece of code that generates code. So typically when you write an application, you could write an application that generates that application. So for example, a for loop could be used to generate 10 print statements or something. And this code generation happens at compile time. So when you compile your application, it will actually for you generate all the code. And it's a pretty dangerous thing because you can circumvent certain rules within the language that this allows you to do particular things. You can circumvent them using macros. So
Macro is compile time code generation.
exactly,
Thank you.
yes. But they tend to be quite a foot gun. So you have to use them when you really know what you're doing. And I think everybody here really knows what they're doing. So one place that's actually, in my opinion, a very good example of when you should use macros is removing repetitive patterns. So when you use macros, you should always use them in such a way that people that don't want to use them can just mimic whatever the macro generates. So here we have an example of examples that are supposed to be run as tests. So the top example subscribes to some stream of events that's defined by txfilter. You run some test code, and then you unsubscribe from these events. Then we have a second example that also is interested in txfilter events. It uses the previous example to generate something like we saw before. And when it's done testing, it unsubscribes. Now the problem is, in Elixir, tests can run concurrently, or they can also run within the same process. So if we imagine that the second example is executing, it will subscribe to some particular topic. It will run example 1, but after example 1, it will be unsubscribed because example 1 unsubscribed. So you cannot arbitrarily nest these things. The solution is pretty easy. You look at your subscriptions before you unsubscribe, and you only unsubscribe if you were not subscribed before running your example. But if you have, I don't know, let's say we have 200 or 300 examples within the code base. If you have to do this 200 or 300 times, that's going to be really painful. So we just wrote a macro that does it for us. And this is, in my opinion, a good example of a macro, because if you don't want to write this, you just write this. Yes, Jamie.
Is this not a failure of the language that you have to use a macro to do this?
I wouldn't say a failure, because yes, maybe it is. And not per se the language, but the testing framework. Because you would expect that these examples run in isolation. So test concurrency is important. I really don't want to care about the execution model of my tests when I'm writing them. So yes, maybe it's a failure in that regard, but luckily we know that that's the way it executes, so we can fix it fairly straightforward. So yes, maybe it's a shortcoming from the testing framework.
This is a functional programming language, so can't you just define a function? If you go to the next slide, please. Can't you define a function that inputs some test code and just wraps it in the stuff on the previous slide? Why do you need a macro for this? You don't have to answer my questions, right? I'm just saying what... isn't this what high-level languages are supposed to allow you to do? Why is this a macro?
I can probably answer that for you. If you were to do it as a function, it'd be very ugly. Like, so typically you make macros because it allows you to change the syntax into something nice. For our normal language example, Python has a thing for opening up files called like with files, and Lisp does too. The reason why you do it is because you have to close off a resource that you created no matter what. And the issue is like, you want to disguise this as not being a function call, because that just looks very bizarre in those scenarios. It would be extra boilerplate. You'd basically pass in a lambda before doing things, and developers don't like passing around lambdas very much.
You're saying you'd have to do some lambda lifting also within the test?
No, you'd have to write a lambda inside the test itself, and that just looks very unnatural. Like, people wouldn't want to write that. It would just you would just have boilerplate, and so macros are a generally normal way of solving this kind of issue, and every language actually deals with this. It's hard not to have this problem, actually.
I think that's kind of the point. So if you use macros, you can take a piece of code and treat it as such. So it's just a piece of that code that you can put somewhere in other code. If you do this at the level of your language, you cannot take a piece of code and move it. You need to wrap it in a function, because that's the stuff you deal with at the base level of your language. But in macros, you can take code as being, it's actually the AST that you have, and you can transform it. So it's a slightly easier on the eyes result than using functions. But you could perfectly do this with functions as well, yes.
To do it with functions, you'd need to go into the syntax of the test code and put lambdas in inconvenient places.
Yes.
Yeah. Okay. So that's the key point. It's not just a matter of taking the test and applying a function to it. You have to manipulate the test. You would have to manipulate probably some kind of lambda lifting pervasively all over the place. Right.
Yes. I think we agree. Yes.
Okay. So for me, that's really, really interesting.
Okay.
I would call that a failure of the language, but it's not of this language. It's a failure of functional programming.
Yeah.
To encode a natural pattern which is arising here, so the programmers are using macros to do it. It's not specific to this language. It's
yeah. Okay. Right. So one other place that macros were really, really helpful is we had all these examples defined in our code base, and we still want unit tests because, well, examples are nice, but you just want to run mix test, which is the test command in Elixir, to just check all our examples. But you don't want to duplicate these examples into a test folder as well. So we wrote a macro. So the use expression here is actually a macro. You pass it a module. So here we have examples e-advertise, which is a module that contains a lot of examples about advertisement. and this macro will generate test calls for all these functions. We excluded here a function to stop some distributed system. So we get all the unit tests for free, as everybody else has. We have just only profit by using examples. So yay macros and yay examples. A few things I think are worth mentioning, but I didn't put in the slides. Erlang has this nice library called Peer, and you can just spin up a cluster of other virtual machines on your system from within Erlang. So there's no need to do it from a CI pipeline or whatever, just do it from within Erlang. The Phoenix framework is a very nice and elegant way to define web applications. And then obviously the observer application, which allows you to just have a graphical interface of the system. You can use it to see the tree of processes I showed before. You can trace function calls. You can connect to distributed systems and inspect all nodes, system load, and all these things. Really good tool. Stuff we're missing, a stepping debugger. It's horrible that it doesn't have it yet. I think we should have one. A proper type system, which is lacking. We have Dialyzer, and that's a very poor static analysis tool. And then maybe a better language server. But yeah. So to conclude, I discussed how you should pick how I think you should pick a language, or at least things you should consider when you pick a language. I showed that Elixir really maps well on the problem domain of the Anoma engines. I showed you how we have transparent network addressing with very little effort. I challenge you to do this in any other language. I explained what examples are and how they are superior in every possible way to unit tests. And I showed you some examples of how we use macros in our system responsibly. Thank you.
Thank you, Christophe. We have time for exactly one short question, not about macros.
Oh.
Jamie.
I will ask my one short question in two parts. Question one, why do you want a type system? Please don't tell me now, but another time I'd be interested in the specific reasons. The other is, so I have a soft spot for property-based testing. I've always liked the idea.
Okay.
But one thing that struck me when I used it was the properties weren't the real gain. Writing the properties you want is nice. It's the generators that really matter, because they force you to think about where the errors are going to accumulate. So for example, a generator for, I don't know, numbers is going to test 0 or -1 and 65,535 because so I wondered if you had any thoughts on what the generators would be, where this is one thing that unit tests don't necessarily capture. Where would the errors accumulate in this kind of system?
So the way I try to think about property-based testing is you can just generate arbitrary values, I don't know, let's say for key pairs. So those are always going to be correct. You just need 32 bytes of something. But as you mentioned, when you start generating possible values for, let's say, quantities in resources, you cannot have negative quantities. So I think that once you start writing these generators, you have to indeed really think about what is the range of the values I can have here. So, and then your question is, how would errors prop up when you write these generators?
Well, you had an example in the talk where you talked about running two examples at the same time, and one of them unsubscribed the other. So to me, that's a really nice example, pun intended, of the kind of thing that a generator could do. It could take existing examples previously generated and then mix them in ways that are likely to accumulate that kind of error.
Well, we actually took care of making sure that these things would run as smooth as possible. So where's the slide? In this example here, so you can see that we pass in a node optionally. So whenever we run an example, and this is because we can run multiple controllers on the system, for every example we start a completely new application. So we shouldn't have any issues with interleavings of examples where you have some previous state or something that was wrongfully generated, because we start from a clean slate every time for every single example. So we shouldn't have any problems with executing multiple examples.
What I was trying to get at is that realistic? Is that the kind of testing you want? Or
Yes, absolutely.
okay.
Yes.
So in real programs, having lots of things piling up on one another and interfering is not something you're worried about?
No.
Okay.
Correct me if I'm wrong, Jeremy.
No, but
No.
no, but if you're interested in that kind of work where you generate out examples which are similar, there was work by a now past mathematician named Douglas Lennart, who made a company called CYC. One of his earliest works, which was recovered like 3 years ago, was called Automated Mathematics and the YAM-URESCO system. And in there, he took Lisp programs, he modified the syntax to define new theorems, basically. So AI finding new programs by modifying the AST. And so, if you're finding error nodes, that would be probably an example of what you'd be looking for if you want to look into a system like that.
Thank you. I think Christoph has answered my question, that this is not a new failure mode. This is something that you're not worried about. So that's fair enough.
Yes.
Thank you.
Thank you again, Christoph.